You ever stop and think about how your brain can be laser focused on one thing and then in a split second pivot to something completely different? It's all thanks to this incredible balancing act, this dynamic dance between order and chaos, between stability and flexibility. Today, we're jumping into that very dance, a core principle of brain function called metastability.
So every single second of your life, your brain is wrestling with this fundamental challenge, right? It has to get billions of neurons spread all over the place to work together, to act like a team to create one cohesive thought. But at the same time, it has to let all its little specialized departments do their own thing. It's this constant push and pull between teamwork and, well, solo genius.
And that, right there, is the paradox. How can the brain be a team player and a solo star at the exact same time? Think about it. When you're watching a movie, your brain integrates everything, the visuals, the sound, the emotions, into one seamless experience. But behind the scenes, your visual cortex is just handling light, and your auditory cortex is just handling sound. How does it all come together without turning into a jumbled mess? The answer is pretty cool. It lies in a state that's neither totally stable nor completely random.
And that dynamic solution is what we call metastability. It's this really elegant principle that lets the brain have its cake and eat it too. It can be integrated and specialized, structured, and yet unbelievably flexible. It's really the secret sauce behind the brain's incredible ability to adapt and respond to, well, everything.
Now, to really wrap your head around what makes metastability so special, it helps to see what it's not. Let's compare it to something called multistability. Imagine multistability as being stuck at the bottom of a deep valley. You're super stable, sure, but you're also trapped. To get to the next valley, you need a huge random push, some kind of noise, to shove you over the hill. Metastability, though, that's like gliding down a kid's playground slide. You might slow down on the flatter bets, hanging out for a moment, but you're never actually stuck. You just flow from one state to the next smoothly, almost by design, as part of this continuous journey.
So, what does that mean in plain English? It means the brain has access to this massive library of different configurations, these different patterns of neural activity, but it never, ever gets locked into just one. It's this constant, graceful exploration that allows for both the big-picture teamwork and the focused specialist functions to exist at the same time. It's the ultimate multitasker.
Okay, before we dive deeper, we gotta clear up a few things people often get wrong. First, just seeing the brain switch between different states doesn't automatically mean it's metastable. A noisy, rigid system can look like that too. Second, the signatures we're about to talk about, they're just the practical tools we use to measure this stuff. They're not some kind of alternative definition. And finally, and this is a big one, a truly metastable system doesn't need random noise to switch gears. It can do it all on its own.
Now, this all sounds great in theory, but you might be wondering, how on earth do scientists actually measure something so fluid and complex? They can't just, look at the brain's complete map of all its possible states. So instead, they have to play detective and look for its fingerprints in the data.
And those fingerprints are what researchers call signatures. By digging through data from tools like fMRI or EEG, they can hunt for these specific, measurable patterns that are the telltale signs of the brain operating in this super flexible, metastable state. So, let's look at a couple of examples. One of these signatures is called STD-KOP. Basically, it just measures how much the brain's overall teamwork is changing over time. If that number's high, it's a great sign. It means different brain regions are constantly forming and breaking up little teams, a clear signature of flexibility. Another one, STD-IGNIT, tracks how a spark of activity in one spot sets off a chain reaction somewhere else. If that's highly variable, it tells us the brain isn't stuck in some rigid, predictable pathway. Information is flowing freely and creatively.
Okay, so why is this so important to measure? Because it turns out our mental health might actually depend on the brain hitting just the right amount of metastability. And as we're about to see, it's definitely not as simple as more flexibility is always better.
Yeah, researchers have found what they call a sweet spot for a healthy brain. The best way to think about it is like a perfectly tuned orchestra. You don't want every instrument playing in rigid, perfect lockstep the whole time. That's boring. But you also don't want total chaos. You want that dynamic, beautiful interplay. The brain is exactly the same. And you can see exactly what happens when the brain drifts out of that sweet spot. Look at this. Studies show that as we age, and in conditions like Alzheimer's, metastability goes down. The brain becomes too rigid, too set in its ways, and it loses that cognitive flexibility. But on the flip side, in conditions like schizophrenia, metastability has actually been found to be higher than normal.
The brain becomes too flexible, maybe too noisy, which could be linked to disorganized thinking.
So that brings us right to the cutting edge of this research. We can see the effects where metastability is out of whack, but the next massive challenge is to be absolutely sure we understand what we're really looking at.
So here's the multi-million-dollar question for neuroscientists right now. When we see the brain switching between states, are we witnessing that elegant design dance of true metastability, or are we just watching a rigid, multi-stable system that's being randomly kicked around by biological noise? How can we tell the difference?
Well, there's a really clever idea for figuring this out called the dwell time test. It's actually pretty simple. Researchers just measure how long the brain stays in any one state before it switches. Now, if the switching is just random noise, the timing is going to be all over the place, totally unpredictable, like a series of coin flips. But if it's true metastability, that graceful slide, the switching should have a more structured rhythm to it, a more predictable pattern. Finding that statistical fingerprint could be the key to cracking this whole thing open.
And that leads us to a really powerful final thought. Metastability isn't just some abstract idea. It's the actual rhythm of a healthy mind. And if we can really learn to read that rhythm, to understand its signatures and decode its dance, well, maybe one day we can develop ways to help a brain that's become too rigid or one that's become too chaotic to find its perfect, dynamic balance once again.